Hey, we're back. This is hopefully the final push to the final. We've got fluid dynamics that we're doing, and we've got what we call a flow rate. And oftentimes you'll see the symbol that we use for rates or rates of change of things or rates of rates. We use Q's. So in this situation for the flow rate, we're using volume divided by time. And in our SI system, our units are going to be liters per minute. That also equals meters cubed per second. And then we've got centimeters cubed per second. But the SI, the only one that's SI, is this one. Okay? So all of those work, and you can do your thing, but if you're going to have other stuff involved and you need to figure out things according to whatever, I would convert everything into SI, okay? And then it doesn't matter at that point. Then you'll have your flow rate in SI units. So how does that work? We've got some area of a tube, and that tube has a certain volume, and let's say we've got this length here, and that length is filled with, that volume is filled with something fluid-like. Okay, so there's our stuff in there. And what are we going to do? We're going to say volume equals our area times the length. All right. And now it's simple. Q is our volume divided by time. Well, length per time, let's say we're flowing in this direction. Length per time is just our velocity, and we'll call it our average velocity. The A doesn't stand for average. The A stands for area. But the average shows up on the bar above the... you don't need it, the bar, but it's nice to have. But we can just say this, and whether you have a line over the top or not, that's fine. But that's the truth. Okay, so all fluids, liquids or gases or whatever, this could be steam, right, going through the pipes. We're considering them to be incompressible. So even though it's a gas, incompressibility is the key. So incompressible in all situations. So anything that we're doing in this class, we're dealing with something that's incompressible because we don't want to complicate it too much. And if we start dealing with compressibility, then we have to add some stuff to our equations. And that's wrong. That's just wrong. Okay, so we want Q to be a constant. So because it's incompressible, Q is a constant. And that's what we want. So this gives us this. So on a test, somebody might say, we consider all of our fluids to be incompressible. Why? It's so that Q is a constant. All right, so nothing is incompressible. I just want you guys to know that. Some things are more compressible than others. And diamonds, for example, are fairly hard to compress. But yeah, I mean, it's doable. Can do. So we take, and we have Q is equal to a constant. What does that mean? That our Q in, so we've got some Q in over here, and we've got some Q out over there. When we go to do those things are equal. So it doesn't matter what the area of our situation is, or the length. It doesn't matter. Our Q is constant. So that means that our area, well, let's do it with the velocity. A1 V1 is equal to A2 V2. And now, all of a sudden, then we can do things like get the ratios depending on what we've got and what we don't have. But we can say V2 over V1 is equal to A1 over A2. So yeah, and all the equations that go with it. So I don't know, maybe you're looking for A2, right? Maybe you're looking for A2. Well, then it's just A2 is equal to V1A1 over V2. So a nice simple setup of ratios for us. Now we can do, and I know that you guys have done, biological examples of this. So you have N. All right, let's do an example where it's the aorta, and then it goes all the way down to capillaries. All right, so we've got all these capillaries. How many of them? I don't know, tons. You can go through and figure out how many there are by using this equation. So over here, n equals 1. So let's say this is n1. And over here, we don't know. There's n2. But if we have n of these things, then we say n1, a1, v1 is equal to n2, a2, v2. And then, of course, we can solve. Maybe we don't know n2. So we can solve for n2, and then we just have n1, a1, v1 over a2, v2. So then, essentially, you'd have to be given all of these things, and then you'd be able to get that. Now, there are tricks, right? I mean, there are tricks to make you calculate first, say, one or two of these things, and then those are tricks of the trade. I can't give away my secrets, but no, I'm just kidding. You could figure it out if you wanted to come up with some challenging problems. I'm sure you guys could do that. You just have to think about what you know and what you don't know. So, of course, the areas of each of these little guys, these areas for 2, those areas have to be very small, right? Because this is our area 1, and that's fairly large. So our area 2 for all of those little guys have to be minuscule, right? So you got to keep that in mind. All right, so let's go down here to Bernoulli's. Good old Bernoulli. and we'll look at his equation. So Bernoulli's equation, you guys know I kind of drilled it into you, but what does it come from? It stems from conservation of energy. So Bernoulli's equation. Well, you guys are probably like, what is he talking about? Well, you know what I'm talking about. Bernoulli's. It is the old P1 plus 1/2 rho V squared. But I'm going to put a 1 on that V. And then we're going to have rho GH1. And then, of course, that equals P2, because why? Why are they equal? Conservation of energy. That's right. So what does that technically mean? That means this whole thing is equal to a constant for the situation. Okay, so it's not, there's not a number out there that all of these things equal to. It's the situation tells us what that will be, and that is Bernoulli's constant. Okay, so we can just write that. It's an energy per volume, but it doesn't matter. Energy per length or energy per whatever is still conservation of energy, right? So that's what we're doing. What are the units of Bernoulli's constant? Well, if it's energy per volume, what is energy? It's a joule or a Newton meter divided by meters cubed. But what is a Newton? A kilogram meter per second squared. So a kilogram meter per second squared times a meter divided by cubed meters. So we can cancel out some things. We'll get rid of all the other two, and we're getting rid of the 2 on top, so we're left with kilograms per meter second squared. And that should hopefully equal what I said in my notes that I posted. So those are the units for each of the terms in Bernoulli's constant. Okay, all of those things have these same units. Okay, otherwise we couldn't be adding and subtracting them together, and we do. So, okay. I think in class you guys told me a bunch of applications for this, but applications, we could use a blowtorch. That's a good one. A spray pump, because well, I mean, you know, you got to fix your hair. And so then there's aspirators, fuel injectors, and airplane wings, because you don't want to fall out of the sky. What else do we've got? We've got jet engines. And there are so many applications. I mean, it's probably literally countless applications. So anyway, there's a lot. Okay. So let's let's talk a little bit about Torricelli's. I really liked it when I did Torricelli's theorem when I first learned it. And even back then, we didn't have the flex tape guy. But we've got something full of water. Okay, so there's the top of the water. And I don't know why someone drills a hole in our plexiglass so they can advertise flex tape. And of course, the water goes streaming out, and nobody's happy about getting water all over the floor. And so then we can immediately slap some flex tape on there. So here's the thing: the open end is open to the atmosphere. So we have the pressure up at the top is atmosphere. We have our pressure down at the bottom is also open to the atmosphere. So that allows us to come back up here to Bernoulli's equation. This pressure and this pressure are now the same. So you can those are gone, right? Those don't matter anymore. They nullify each other. So we end up with the old remainder of what's happening left. Secondly, H2 doesn't factor in at all because H2 we're going to consider as 0. So, man, things just start dropping out. Torricelli was a good man. Got us all dropping out all these terms. And what do you have here? Oh, look at this. Rows in each term. So imagine that. And then we can multiply this guy by 2. Get rid of all the halves. So what do we got? We multiplied everything by 2. So we've got V1 squared plus 2GH1 equals V2 squared. Oh, that's manageable, right? That is really, really a nice way to handle it. And that's exactly what I wrote, I hope, in the notes. Yep, there it is. So, Torricelli's, right? That works out. So we'll put a cap on that. And we'll move on here to power in fluid flow. So how are we going to get that power? All right, well, let's talk units first. Power, we know, is in joules per second because power is energy per time. So it has to be joules per second, and that is equal to a watt. I do watts like this with the upside down mountains, sharp pointed mountains, because we need to kind of distinguish work from energy or from watts. So now we can look at Bernoulli's constant. What's up, B? Bernoulli's constant is energy per volume And since we have Q is equal to volume per time, all of a sudden we can multiply Bernoulli's constant. We can multiply it times Q, and this volume and that volume cancel, and we're, lo and behold, we're left with energy per time. So we've got energy per time. How about that? That's nice. And everything's incompressible. So Q is something that we can come up with. B's constant is something that we can come up with, Bernoulli's. And man, we're done. We're off to the races. So we can get our power for a situation by taking our P1 plus 1/2 rho V1 squared plus rho GH1. Slap a Q on top of all that. So what does that mean? It's the distributive property. So Q, excuse me, Q is going to be multiplied by this, by this, by this. And that's going to equal our power for the situation. Keep in mind, this thing is a constant. This thing is a constant. So they're both constants. Having them both be constants means it doesn't matter where you get the information from. If you get it from the beginning or get it from the end, one side is as good as the other. So you can come back here to our our situation here, and you could say, oh, I want Bernoulli's here. So let's get B's number there, and then we can get the Q from over here, or vice versa. Or we can get them both from one side. It doesn't matter. But either way, you're going to get, if you take any of those numbers, B's and Q's, they should all be the same. You take those numbers and you can multiply them together and get your power. All right, so let's move forward. Moving on up to the east side, to the old deluxe apartment in the sky. Viscosity and laminar flow. We've got viscosity. Let's do viscosity first. Let's handle viscosity first. The symbol for viscosity is eta. So we've got our eta, and viscosity is units wise is what I want to say. Units are meters, pascals, and seconds. Oh wait, no, not meters, millipascals per second. I was thinking that's kind of odd. Okay, yeah. So millipascals. What is milli? Not the partner to vanilli. Milli is equal to 10 to the minus 3. So what we're saying with millipascals is, a millipascal is we've got 10 to the minus 3 pascals. And we're multiplying that by a second. Okay, so millipascals times a second. That is viscosity. These are the SI units. Table 12.1 will have viscosities. You don't need to worry about that probably anymore, because I'll be giving you viscosities on the test, so you don't need to worry about that a whole bunch. So now, in laminar flow, so we first have to describe the situation. Okay, so here's the experiment. They want to know what, oh gosh, what's an exotic fluid? Something that flows, but we want to know what the viscosity is of it, but it's not a very popular fluid. Let's say it's paint, okay, but it's a paint that is a mixture of latex paint and water-based paint. Oh, I don't even know why you would do that, such a thing, but whatever. So we've got this new product, and we want to do the old testing for viscosity, and we take two plates, and we have a bottom plate and a top plate, and we apply a force to the top plate. All right, so in between are layers, and I've just drawn them as layers so that we can kind of, it's not all one big fluid, but layers of fluid. But it really is all just one big fluid. And we're going to apply that on top, and we're going to measure the fluid, or excuse me, the force on the bottom plate, okay? But at any rate, the force that we have to push is equal to our eta times our velocity, is it velocity? It's got to be velocity. All this time, why don't I know this? Newtons. It's got to be velocity. What? I don't like that this isn't rolling right off the top of my head. I don't think it's a volume, but I don't want to steer you guys wrong. I want to make sure that we don't do this wrong. Torricelli. I never got to tell you guys. Look up Torricelli, because that guy is really, I think Torricelli's pretty cool. You know what it is? I didn't just talk to you guys about it in school because I didn't have my notebook. So now that I do have it, now that I do have my notebook, I can get into it, but I don't do these types of equations very often. So let's erase what we got here, and let's do the full presentation. We've got some volume in between these two plates, okay? And there's a length between the two plates, so there's a length from here to there, a width if you want to say that. This plate has an area, this plate has the same area. We're applying a force to the right. What do we have on the left, we've got the force of friction. Okay, so the force of friction from this viscosity of the fluid is holding us back. And we're going to push to a point where the force of our press forward and the force of friction are balancing out. What does that do? That gives us a static situation. We are now in a place where we've reached terminal velocity. Okay, so terminal velocity happens, and our force of friction is equal to that. So what does that mean? That means there's no acceleration, and we're at v is equal to a constant, or our terminal velocity. Okay, so our v is equal to a constant. So that is the v that we're looking for. And which is great. And so then we say, all right, well, our force that we're applying, now keep in mind, some theorist, wasn't me, went in and they figured out that eta times our velocity times the area divided by L, the length, the basically the width of our channel of flow, that all equals our force, okay? And you might think of it as the same thing as saying it equals our force of friction, all right? That's another way of looking at it. So V, not hard to measure, okay? Our area, easy. We can measure that. Our length, easy. Or width, however you want to think about it. So the only thing we really don't know, because the force is easy to measure too, right? You guys have measured forces. You just get the little box and you hook it up and pull on it, and you've got a measurable force. So we don't know eta, right? But that's what we really want to find out for our newfound paint, our newly developed paint, because we got to put it in cans, we got to process it, we got to push it through pipes, we got to get it all the way from the big huge vat that we mix it in to little individual cans of paint. So in order for us to do that, we need to know what this viscosity is for the paint. So we've newly developed this paint. So then we say, oh, good, all right, well, I can rearrange that equation and say that eta is equal to F times that height of our fluid, or width of our fluid flow, and then we're going to divide out by our velocity and our area. So all of those, we do our experiment, all of those things have numbers, we end up with some new eta, okay? Some new, a newly found for our newly developed paint. All right, so yes, this is done with shampoos, lotions, food of all kinds, because seriously, all of our food gets processed through these pumps. I mean, just the pump itself needs to know what the viscosity is, right? Because it's going to be pushing with fans or turbines, pushing that fluid through, to just run a pump on something, you need to know what the viscosity of it is. Okay, so I think we killed viscosity. What causes flow? Well, there's a few things that cause flow, but mostly it's a difference. So we have P over here, P1, and over here we've got P2. And the only reason that we're going to have flow is because P1, if the flow is going in this direction, P1 is greater than P2, right? If they're equal, are we going to get flow? If P1 equals P2, do we get any flow? No. So you gotta have a difference. You gotta have a delta pressure for flow to happen. So your meteorologist, your local meteorologist, he comes out and he says, "Oh, winds are going to be high today." So what does that mean? If winds are going to be high through, all right, so here's the Front Range, right? We've got Denver, and we go to school down here in Castle Rock, and there's people who go to school up in Fort Collins and Boulder, even closer to the mountains. So in order for there to be high winds, and typically the winds go like this, okay, so from west to east, so that's our wind. If we have winds happening, that means that our pressure 2 over here is less than our pressure 1 over there. As soon as that happens, winds develop, and because the fluid here wants to get away from that and go to a place where it's lower, okay? So therefore winds happen, and all pressures change, right? Because these vortices of pressure, those move about the country as well, right? They have their own path and do their own thing. So winds change. I mean, it could be that this is the high pressure over here and here's the low pressure, and we'll have a situation where the winds are going like this. So that happens too. So winds come and go. Oh, what remains are the values of culture. So that's fine, but now we've got this fluid flow. We've got flow happening. So we've got a velocity, and if the velocity for the situation, let's draw a situation. We've got a tube, and our velocity is greater than a critical velocity, V critical. I don't want to say just C. Let's say V critical. When it's greater in this situation, okay, so we've got our velocity going through, that laminar flow that would normally be there, okay, we've got layered flow, smooth layered flow, all of a sudden develops in these eddies. Eddies start to develop, and what do you know? What happens when these curlicues start happening and make things? Well, it balls up. It definitely slows down your situation, and it keeps the velocity from being greater than it should be normally. Okay, so you have dissipation of the excess energy. Okay. So nice, right? Awesome. So here we have stratified, okay, no turbulence, laminar, no turbulence. These are just synonymous things. No eddies. No ed or eddies. And on this side, we've got turbulent flow. So turbulence. And we can't say that it's stratified, laminar. We certainly have eddies, right? We just don't have Eddie Van Halen anymore. So there is our situation. Now, why would an obstruction cause this to happen? If you have a laminar flow in a situation and we're keeping the velocity equal to or less than, so less than or equal to some critical velocity, but we stick a obstruction in the middle, right? Well, that removes some of the area that we're able, our area is now area 2 instead of area 1 that it should be. So our area 2 happens, what do you get? You get a higher velocity because of that. So through this region where the obstruction is, our V jumps and is now greater than VC. Okay, so our situation then gives us trouble just because we have this darn obstruction in there. And next thing you know, you've got a situation like this. Now, it could turn out that once the velocity slows down again, it gets to a point where it's less than VC, and then that's great, and it'll return to laminar flow if it's allowed to slow down. But otherwise, we're in this situation where we've got a foamy, eddy-filled flow, okay, that is keeping our velocity where it should be. So obstructions and then higher speeds or rates of flow cause turbulent flow. I did talk about the differences in flow already. And since we have differences causing our flow, so we have our final, we have our initial pressures. So here's our P final, here's our P initial. Again, giving us a delta P. We can do a thing where we do a little math, and we've got our Q equals our volume of flow per time. But it turns out, believe it or not, if we do this right, we can get our delta P. And if we divide by the resistance, so what keeps our velocity at a critical maximum velocity? Resistance, okay? And resistance doesn't allow us to go any further or faster, right? We have this resistance. So delta P over R is our resistance to flow, and that gives us a nice equation. So our Q is equal to P final minus P initial over some resistance for that fluid. So the higher the resistance, the lower the Q. All right? The larger the difference in pressure, the higher the Q. So they are definitely, and technically, this should be negative, right? If our flow rate is in that direction, we need to put a negative sign on there. So, yeah, don't tell my notes or the book if they have it backwards as well. But maybe I'll fix my notes. But at any rate, yeah, our P final has to be lower than our P initial for the flow rate to go in this direction. Let's get this direction, flow rate. All right. All right, so what increases our resistance? Well, we already found viscosity, right? So our viscosity causes our increase, and it turns out that it's linear proportional to our resistance. Another way to say that is resistance, because that's what we're trying to find, is proportional to our viscosity. And it turns out that our resistance, we're not going to derive it. It's a complicated situation, but we learn it in school, and then when we go get an engineering job at the paint plant, we can go through and figure out our resistance for a certain thing because we did the work and figured out our viscosity. We measured all of our pipes, and we found the radius of all the pipes, and of course we learned about 8 in like second grade and pi in 5th grade. So all in all, we can do this. We figure out our resistivity, and it all kind of hangs together. And we can talk about it, but if the length increases, our resistance increases. If the width or the radius of the pipe itself increases, it reduces, right? So the wider the pipe, a small pipe, this small one right here, isn't going to be as good as this bigger pipe that is going to allow for more flow. Not only will it allow for more flow, but it'll allow for faster flow, okay? Because in the end, our flow rate increases inversely proportional to R. So as that radius goes up, our Q definitely can go up. So that's nice. And then our viscosity. It's definitely directly proportional to our viscosity. And that's the equation that we like. So let me write it nice and clean so it doesn't have all that garbage. We've got eta, we've got L, we've got pi, and we've got R to the 4. Okay. So we are almost home, guys. Almost there. What do we have left? We can combine. Let's drop down a little bit. Let's combine some stuff. And we're going to combine our Q, which equals delta P pressure, delta pressure, over R. And R is equal to this thing. We'll combine them, and we'll get that Q is equal to our delta P pi, that's to the fourth, our radius of our pipe to the fourth, times 8 times eta times our length. And that, my friends, is the end, because this right here is driving our flow rate, okay? That delta pressure, which would be our P final minus our P initial. In fact, because delta equals this, and there's no way that you're going to have a final pressure, no matter what happens, your initial pressure, you're always going to be flowing in this direction. So no matter what happens, your final pressure is going to be less than your initial pressure. Well, if that's always less than, this is going to be negative. Well, that's going to give you a negative flow rate. So we have to put a negative sign in the front of this. And I don't know if the book does that or not, but I'm going to do it simply because this equation will be negative if your velocity of fluid is going in that direction. This will be lower than this, so P final minus P initial will be negative. So we got to have a negative sign here. Okay, so make sure that you don't get that backwards. And that, my friends, is it. I'm going to see you on Monday. So take care. Peace out is what they say in Hollywood.